Hello, and welcome to Lecture 16, Part 2 for Life in the Universe, where in this video, we're going to look at why we want telescopes to be as large as possible. So there are two reasons why we want big telescopes. One is that bigger telescopes have better angular resolution than smaller telescopes. So this is a measure of the finest detail that the telescope can see. So this parameter right here is the Greek letter alpha, and it represents the smallest angle that can be resolved by the telescope. The smaller that is, the finer the detail we can see, so we want that to be small. Okay, don't worry about the value of the constant. That depends on the geometry of the telescope in a way we don't need to worry about. See that angle is proportional to the wavelength at which we observe. And at least as long as we're talking about visible light, wavelength doesn't vary much, so that's not a big problem. But when we go into other parts of the spectrum, we'll see that does matter. And then divided by the diameter of the telescope. So it's because the diameter of the telescope is in the denominator, the bottom of the fraction. The bigger we make the diameter, the smaller we make alpha, and the finer the detail we can see. Now, there's a slight problem for this if we're using a telescope on the ground, and that problem is that the Earth has an atmosphere. Now, I don't want to complain about the atmosphere too much. I like breathing. However, I'd imagine many of you have noticed this phenomenon, say on a hot day in the summer, where if you look over a roadway in the sun or the hood of a car in the sun, and you see how things appear to shimmer. Okay, that's because the air above that heated surface is very turbulent, and the light passing through that turbulent air has its path deflected. That phenomenon is always there, although it's relatively rare that it's strong enough where we can see it with the unaided eye. But with telescopes, because you're magnifying everything, you're going to notice it. Astronomers refer to this phenomenon as seeing, the blurring out of things because of atmospheric turbulence. So if you hear one of us say that the seeing is particularly good tonight, that means the air is relatively stable and the images are fairly sharp. Scintillation, which is the what's behind the twinkling of stars, that little variation in brightness, is also an atmospheric turbulence effect. It's related to seeing, but it's not quite the same thing. Well, anyway, because of this atmospheric turbulence, a telescope on the ground, even if you are at the best ground-based sites, so way on top of a mountain somewhere, this is going to limit your resolution to nothing smaller than roughly half an arc second at best. And the thing is, you don't need a very big telescope to give you a resolution of half an arc second, only about 9 inches. And so if you don't correct for this, any telescope 9 inches or bigger is basically going to give you the same angular resolution. Now, the Hubble Space Telescope, which I'm sure you've heard of, is not a big telescope by ground-based standards. It's only 2.4 meters in diameter, very modest for compared to ground-based telescopes. But because it's in orbit a couple hundred kilometers up, it's above the atmosphere and it doesn't have to worry about these distorting effects. So right here we have two images of the same object. It's a massive unstable star called Eta Carinae, and it is uh, over the last few hundred to few thousand years, it's expelled some gas, and that's what the blob is. The picture on the left is a ground-based image, and the picture on the right was taken with the Hubble Space Telescope. And you can see how much more detail shows up in the HST image as opposed to the very blurry ground-based image. But I think even more than just the detail you see on the clouds of gas expelled by this unstable star, look at the other two stars in the image. On the left, the ground-based image, we see them as these two really spread out fuzzy blobs. But on the right, we see their nice sharp points. And even to the Hubble Space Telescope, most stars are unresolved points of light. You can see how much sharper those points are in the HST image as opposed to the um, ground-based image. And you can see kind of what an advantage it is in terms of angular resolution to get above the atmosphere. Now, if, oh, I should also point out, I almost forgot this. Yes. in the last 2 to 3 decades, we've come up with these techniques we call adaptive optics, where we can largely correct for the effects of atmospheric distortion. Now, to do that, we need a fairly bright point source of light in the sky close to our target. And occasionally there will be a bright enough star to do that, which is great, but usually there's not. But fortunately, there's a way you can make a point source. You can think of as an artificial star wherever you want to by using a laser to excite sodium atoms in the upper atmosphere. And that little glowing spot of sodium atoms then will provide a point source so you have a reference to know how to correct the light. And it has this added cool feature that the laser beam looks really, really neat when it's shooting out of your dome while you're observing. So this shows one of the telescopes in the European Southern Observatory facility called the VLT. It's an 8-meter telescope equipped with adaptive optics, and so you can see the laser beam shooting out of the dome. And when you compare what that 8-meter VLT can do with adaptive optics to the 2.4-meter Hubble Space Telescope above the atmosphere, is they're pretty comparable. In terms of the fine detail on something extended, like on the clouds of gas, I think the HST is better. But at least on the point sources, you see how sharp those two stars are in the adaptive optics image. And actually, probably even a little better there than they are on HST. Okay, but this is something we've only been able to do for the last 20 to 30 years. And we've been building telescopes larger than 9 inches, with about where you get the limits for what the atmosphere will do for you without adaptive optics, for a lot longer than that. Actually, going back well into the 1800s, we built telescopes bigger than that. So that means that big telescopes must have some other advantage. And to think about that, think about, say you're trying to catch rain in a bucket. What kind of bucket do you want to use that's going to let you catch the most rain? And a bigger bucket with a bigger aperture will let you catch more rain. Well, think of a telescope as a light bucket, except you're trying to catch photons instead of raindrops. So a bigger telescope will gather more light. And the surface area of the aperture of the telescope will be what determines how much light you can catch. In other words, that will be proportional to the diameter of the telescope squared. And as a representation of that, here we have 2 pairs of images. The top one is of a star cluster. The bottom one is a picture of the Orion Nebula. And here we are looking at the images on the left were taken with a smaller telescope. The one on the right, similar detector, similar exposure time with a larger one. And that larger telescope collecting more light lets you see fainter things. So you can see fainter things with bigger telescopes because they have better light gathering power. Now, to give us a comparison of light gathering power of some existing telescopes, this shows to scale diameters of a number of telescopes. The little dot you see right here, the first thing under WSU, that's one of the little meaty TXs like I was showing in the previous video. You know, 4 inches in diameter. We have a couple of larger telescopes. We've got an 8-inch and a 10-inch. And if we were able to meet in person this semester, if my schedule and the weather allowed it, we'd try and get one of those out for some stargazing. I'm sorry that that won't happen this semester, but you know, got to deal with it. Now, for the other one with a question mark over it. If you haven't ever done this, go on Google Maps and look at the satellite image of campus. And you'll notice on top of Wilson Hall, where we would normally be meeting, there's a nice round circle on top of the building. And the reason that's there is that when Wilson Hall was designed in the early 70s, built, I guess, mid 70s, 74, 75 when it's opened, the original plan had a rooftop observatory. That blank circle on the roof tells you that at the time they decided, you know, we could save some money if we just did the observatory later. And unfortunately, later hasn't happened yet. Since I've been at Westfield since '99, we've had a couple of chances of bringing it forward. First, maybe around 2002 or three or so, I forget the exact year, we started looking into the possibility of making later happen, and I even wrote a grant proposal for to build a dome and a 16 to 20-inch telescope. What's shown there, that would be a 20-inch telescope, which would be about the biggest that I think would be worth having, given the light pollution we'd have around campus. And anyway, the first proposal, wasn't successful, but next year we were working on it some more, and the VP of facilities pointed out to us that the elevator does not go up to the fourth floor or past the fourth floor. It does not go up to the roof in Wilson. And that meant that to make it properly accessible, we would need to extend the elevator, and that increased the price of the project by a factor of 10, which is why we stopped pursuing it at that stage. And then several years ago, when we were in the design stage for what's now the Stevens Science and Innovation Center, that addition on Wilson has all the nice new labs. Uh, the VP of facilities pointed out, hey, now probably is the time to think about the observatory. And we were thinking about putting an observatory on the roof of the new construction. But then it became a thing where we found out how much money we actually had. The original plan, you probably don't know this, had actually called for not just building the new building, but the existing Wilson Hall was going to be completely gutted and redone. And just look around in Wilson Hall, you see that didn't happen for the most part. All we did with the old Wilson Hall is where the labs used to be. We renovated those. So, for example, where the math department offices are now, those used to be chemistry labs. But given that we had to cut the cost, that was one of the things to cost. So maybe someday, but we don't have it yet. Okay, the next one is that's Fierke's refractor, 40 inches or 1 meter. Then we have the Hubble Space Telescope at 2.4 meters, and the circle in the center indicates the shadow of the secondary, which you really should consider. And then we have Palomar, so 200 inches, 5 meters. And as we said, about 8 meters or a little bit bigger seems to be the limit for a single piece of rigid glass. But we've learned over the last, well, actually around early 90s is when the first segmented mirror telescope, the Keck 1, came into operation. And Keck 1 is 10 meters in diameter, made up of these hexagonal segments. Now, in order to have a segmented mirror, first they had to develop the techniques to actually make each segment have the right shape, because they're all off axis, so it's not symmetric. And each segment has to have its position adjusted a couple of times per second by computer controlled motors on the back of each segment. I think each segment has maybe 3 motors on it in order to keep the overall mirror the right shape. So Keck 1 cost $70 million to design and build. And then they built a twin of it, Keck 2, that only cost $30 million, because once you've done it once, the second one's cheaper. And both Keck 1 and Keck 2 are on top of Mauna Kea in Hawaii. All right, this gives you some idea of where things may be going in the future. The red boxes that you see here are around some that we talked about previously, including both Kecks there. Also to scale, sorry, I lose the track of where the little pin cursor thing is. That is a tennis court. That is a basketball court. And there's an adult human right there. So the biggest one currently operational, I lost there it is this one in South Africa called SALT, which is about 12 meters segmented mirror. And but then we've got 3 under construction that are kind of the next generation of very large telescopes, and I'm circling them here. And so the smallest of these, which is the one down, lost it again. Here we go. Down here, the Giant Magellan Telescope. It will have 7 individual 8-meter mirrors, which will all send the light to a common focus, giving you the equivalent of about 26-meter diameter telescope. and that is currently under construction. The next one in size is running into some interesting problems. That's a 30-meter telescope. By the way, these planned dates for completion are out of date from this few years old. Anyway, 30-meter telescope, that tells you the size of it just from the name. The plan is for that to go on top of Mauna Kea in Hawaii, and that's the problem. Even though there are a lot of telescopes already on Mauna Kea, and it's been decided that the 30-meter will be the last new one built. Anything else new that goes there will have to replace an existing one. But there has been significant opposition to continued telescope construction on Mauna Kea from some native Hawaiians. Mauna Kea being a holy mountain in Hawaiian culture. And the problem with this is you have here a conflict between completely different value systems that you can't really decide how to give weight to one or the other. And maybe as an analogy, it would be like asking what tastes better, or Corvette or Hamlet. You've got completely different things that that the criteria for judging their worth would be completely different. Um, and I don't know what the answer to this is. I know I know of one native Hawaiian astronomer who's in favor of it because celestial navigation was a big part of how the Polynesians managed to colonize the Pacific Islands and reach Hawaii. And so his argument is that doing astronomy on top of Mauna Kea is a great way to honor the ancestors of today's Hawaiians. Um, but then on the other hand, when I think about what to me is most sacred, it's libraries and observatories. And if somebody was going to do something that would, in my mind, damage an observatory, I'd very much be against it. Anyway, it seemed like all the legal problems had been circumvented for construction, including a ruling from the Hawaii Supreme Court that it could continue. But then rather significant protests managed to stop construction. I'm not quite sure what the current status of that is. They do have a backup site in the Canary Islands. And sometime before the legal issues had all been worked out, I saw at a meeting a guy from who on the project, and I asked him whether he thought it would end up on Mauna Kea or in the Canaries. And he said at that time that officially they were still saying Mauna Kea, but he suspected they'd probably have to go to the Canaries. The mountaintop in the Canary Islands isn't quite as good a site as Mauna Kea, but it's pretty good. So the science wouldn't be impacted too much. And anyway, maybe the best thing would be just say to go ahead and move it to the Canaries. The last of these, the European Extremely Large Telescope down here, or the ELT as it's now called, is under construction in Chile. It's being built by the European Southern Observatory, which is a consortium, number of European countries. Chile is generally happy for other people to put telescopes on their mountains because they typically have a condition for that, is that Chilean astronomers have to be guaranteed some of the telescope time. The original design called for a 42-meter mirror, but then I think they figured out they could save a significant amount of money by leaving the outer ring of segments off and not have a significant impact on the science. Anyway, it's hard to get a feeling for how big this thing is. So this is one of the ESO's publicity pictures. So it shows the ELT dome to the same scale as the 4 individual domes for the VLT that each hold 8-meter telescopes. And then over here we have the Arc de Triomphe, major landmark in Paris. There's a version of this with the Brandenburg Gate, I guess, for German consumption, since Germany and France are both members of the ESO. But I thought I came up with my own way to try and really give you a feeling for the size of it. So you remember in the last lecture, we talked about the Yerkes refractor. And I showed you this picture. And so here I am down in the lower left with the Yerkes refractor. This dome is 90 feet in diameter. Okay, so here is the Yerkes dome to the same scale as the ELT dome. And notice that the entire Yerkes dome would actually fit inside not just the ELT dome, but in the ELT telescope mounting structure. And so this is something that is really kind of absurdly large. Um, it's not cheap. The estimated cost to build the ELT spread out across about a decade is about €1 billion, which is about $1.3 billion. I'd have to check the most recent exchange rate, but somewhere around there. Um, Now, I'm sure that $1.3 billion sounds like a lot of money to you. If it does not, please contact me immediately to discuss your donation for the construction of the Westfield State University Observatory. But the thing is, unless your name is Bezos, $1.3 billion probably is a lot of money to us on individual scales, on the scale of individual people. But on the scale of what people do collectively, it's not much. And let me give you some examples. And my point here is not saying that we have to choose between these, but the point is, it's just compared to other things that people do collectively, $1.3 billion is quite reasonable, especially if you spread it out over 10 years. So for maybe something that's also fairly important besides science, the city of Springfield, near Westfield, is a city I would describe as a small, big city. I think that's a good way to think of it. And anyway, at least a few years ago when I looked, the budget for the public school system of Springfield was about $130 million per year. So about the same as the annual cost to build the ELT. So for the same amount of money to run a small big cities school system over 10 years, in the same amount of time, you can build the ELT. I have an aunt who's now in her mid 80s, so she's long retired. But when she was working, she was the secretary for the superintendent of the Cobb County school system in Georgia. And Cobb County school system is one of the bigger ones in the US. It's not the biggest, but it's a pretty big one. And a few years ago, I checked, their annual budget was almost $900 million. So for about a year and a half of running the Cobb County school system, you could build the ELT. And again, I'm saying we don't have to choose between them. It's just that, show you that it's comparable for things that we consider worthwhile. Maybe something a bit more frivolous. Each Avengers movie individually had box office receipts enough to build the ELT. Uh, for Avengers Infinity War and Avengers Endgame, either one of those movies for what were the ticket sales would have been enough to build the ELT twice, and with some left over. So I think if we can spend that much money collectively to see Avengers movies, then it's not a bad idea to spend this much money collectively to build a telescope. All right, that's the end of this lecture and our code for today. So I'm recording this on October 8th, 2020. The great guitarist Eddie Van Halen died a couple of days before I recorded this. And in his honor, I'd like to make it the years in which I saw Van Halen perform live. Saw them when I was in high school back in 1980 and 1981. By the way, these are not the tour t-shirts that I had. Those have long since died. The oldest tour t-shirts I have are from the 90s. But anyway, I've found these, I think you can still buy them on eBay if you want. But anyway, so in honor of Mr. Van Halen, here is 1980 and 1981 is this video's attendance code. Okay, so that's what I got for you for this lecture, and I'll let you know when the next set of videos are available.